All right, so let's tackle the first page. So, question one. A rock is thrown vertically upward with initial speed v naught. Assume a frictional force proportional to minus v, where v is the velocity of the rock. Neglect buoyant force of air. Which of the following is correct? So just scanning those. The acceleration, speed. So it's asking mainly about the acceleration and the speed. So little quick diagram. I throw the rock up. V naught, forces acting on it are V gravity and V friction. So if I sum those forces together, the gravity is pulling and it's going to be helped by force friction. If you're going to add them together, now MA equals minus mg plus a minus v mu. Just rewrite this a little bit. MA minus mg minus v mu. Then I can get acceleration just by itself. 1 over m minus mg minus v mu. Okay. Now, let's start looking. The acceleration of the rock is always equal to g. Well, you can clearly see it's not, so we can scrap that answer. Acceleration of the rock is equal to g only at the top of the flight. So if we're at the very top of the flight, then v is going to be equal to 0. So if I plug in v equal to 0 into there, I end up with a equals 1 over m minus mg minus 0, boom, boom. A is equal to minus g. That's potential. Let's go to the next one. The acceleration of the rock is always less than g. We just proved that's wrong. The speed of the rock upon its return point is v naught. That is not true. The air resistance is going to act upon it, slowing it down, so that's not right. The rock can attain a terminal speed greater than v naught before it hits the starting point. That is incorrect because you have to take in conservation of energy. It can't gain energy unless acted upon. The only thing acting upon it is gravity, which is slowing it down. So nope. So we were right. It looks like B is the correct answer. Now let's move on to the next question. Let's see. A satellite orbits the Earth in a circular orbit. An astronaut on board perturbs the orbit slightly by briefly firing a control jet aimed toward the Earth's center. Afterwards, which of the following is true of the satellite's path? It is an ellipse. That's probably right. Hyperbola. No. If we look back into the question, they mention slightly and briefly perturbing it. Those are kind of important. It would have a lot more or the thrusters would have to be much greater for it to have a hyperbolic motion. Circle with a larger radius. No, it sounds reasonable, but if the orbit kicks out, so if I have the orbit here and it's going, let's pretend this is going to be circular. If I have that thrust, force of thrust there, what's probably going to happen, or what's going to happen is it's going to return to this spot, but it will have a wider orbit. So now it looks like it's probably going to be A. Kind of convinced myself just by that little drawing and thinking about it for a second. Hyperbola is no good. That doesn't sound right. Spiral in. Nope. If it's spiraling, that would have to be a continuous force. You would have to constantly keep pushing out, out, out. There would always have to be an outward or an inward thrust in order to create a spiral. Um, and oscillations per revolution. That doesn't sound right. If you have an orbit and you give, or any stable orbit is only going to have this kind of path. It's not going to oscillate around that unless there's something else going on with the orbit. So I think I've convinced myself that A is the correct answer. All right, and let's go to the next question. For blue light, a transparent material has a relative permittivity, a dielectric constant of 2.1, and a relative permeability of 1.0. If the speed of light in a vacuum is c, phase velocity of blue light in an unbounded medium of this material is something. So this is kind of unfortunately just an equation check. You could use a little bit of logic on that, I've seen, but for the most part, it's just do you know the equation for phase velocity. So if you have the phase velocity, it's going to be the energy over the momentum. And let's write down some things that were given real quick. Epsilon naught, the permeativity is 2.1. Mu, the permeability is 1.0. So using this equation here, we want to know that E energy is going to be mc squared over 1 minus v squared c squared, or just gamma mc squared. The momentum, very similar, is mv over 1 minus v squared c squared, or gamma mv. Then plugging those back in, I get the phase velocity is equal to gamma mc squared over gamma mv. Cancel those two out. Phase velocity is equal to c squared over velocity. There's one more equation you kind of have to know. I'm just going to write that here. That the velocity of a light particle is given by the relation of the permeativity and the permeability. I always get them mixed up. They shouldn't sound so similar. Side tangent, but plugging this into here, I get that the phase velocity is c squared over epsilon mu. But looking at their answers kind of over here, they want them something to do with a square root. So if I look at that, I have phase velocity is equal to c over the square root of epsilon mu. Plugging in our values up here, we get that the phase velocity is c squared times root over root 2.1, which is d. So all these are no good. A quick little sanity check I have seen with this. This isn't my first go through of these. God bless recordings. I always mess these things up, but I decided to not care as much and just go with it. So a good sanity check I saw with this one is the phase velocity on that one would be greater than c, which doesn't make any sense. Same with that, phase velocity greater than c, boom. That one is about c. That one's also about c, but this one is like half c, which is pretty small. You wouldn't expect it to slow it down that much. So you kind of have a 50-50 check on those. If you don't remember the equations, that's one of the physics GRE is it's mostly, I should say mostly, there's a lot of did you know this equation? And that was always something I was, let's just say, not the best at. I had a professor actually tell us not to memorize things. If you could derive it, you were good. So maybe I took that a little bit too far. So, question 4. The equation y equals a sine of 2 pi t over capital T minus x over lambda where a, t, and lambda are positive constants, represents a wave whose. So this is, again, kind of a do you know the equations, but more of a do you understand the basic form of an equation. So with the wave equation, uh, y equals a sine, I'll just write the whole thing out, y to pi t t x, not y, I don't know why my brain did that upside down, lambda, the amplitude is going to be this value here. So we can kind of get rid of that one right away. The velocity is in the negative. This negative sign right here actually represents a positive movement. Positive movement. So that one is no good as well. Period is t over lambda. Just looking at some dimensional analysis to kind of finish this rest up, we know that period is supposed to have seconds, but here we're given t, which is often just the period, over lambda, which is going to be equal to seconds over meters, which does not give us. So for these two, they're both giving us a speed, which is going to be meters per second. So I have x over t, which does give meters per second. And then I have a lambda over t capital, which also gives us meters per second. So which one? If I look at this, it's a position over a time. So if I think of that, even if I have some kind of underlying wave, boom, ignore the terribleness of the wave. Think of it as a particle moving along the wave. It's asking me the position of that particle over time. How much is that particle moving over time? That doesn't necessarily tell me the moment, geez, fumbling words, the speed of the wave. It tells me the speed of the particle moving along the wave. This one asks for the wavelength over a period. So if I take a wavelength, it's asking me how many wavelengths pass that point over a given time. So that's no good. This is the speed of a wave is given by lambda over the period. All right, making decent progress. Now I think, yep, last one for this page. So I like this one. Let's read it. Two small spheres of putty, A and B, of mass m and 3m, respectively, hang from the ceiling on strings of equal length L. Sphere A is drawn aside so that it is raised to a height of h naught, as shown above, and then released. Sphere A collides with sphere B. They stick together and swing to a maximum height h equal to. So break this problem down into two pieces. You have part one and a part two. Part one is going to be kind of all the stuff that happens before the collision. So the drawback and right up to the impact. So we want to find a relation between the velocity and the height. So let's just start writing some things we know. So when it's pulled back at the top of the pull, all of the energy is potential. Then, right before it hits, all of the energy is kinetic, and that the potential is equal to the kinetic. Since it's a conserved system, energy isn't being pumped into it. So I can set up something real quick with that, where I have mgh naught is going to be equal to 1/2 mv naught squared. So let's solve for the velocity, because that velocity is going to matter, as it is the velocity right before the impact. So if I mess around with that, that cancels, so I end up with v naught is going to be equal to square root of 2 gh naught. Now let's do this. Let's break it down a little more granular. So one is before the collision, 2, so let's write before collision, and this is, ugh, I don't know what letter I was trying to write there. This is the collision. So that's where we're going to shift to a momentum. So I'm going to have the momentum at 1 is going to be equal to the momentum at 2. So using that, let's see if I can save a bit of room. I ran out of room last time. If I have mv naught is going to be equal to 4m, because I'm adding them because it's a, what is it, inelastic collision. They stick together, times v final. So taking that, I have m, and now I get to plug in this value up here, 2gh naught equals 4m v final. Cancel, cancel. I'm trying to solve for the final velocity so I can work with part 3. That is going to give me a final velocity of square root of 2gh naught over 4. I'm going to pull everything into the radical. Get me 2gh, and I have to square that for 16. So final velocity is going to be that number there. Now on to part 3. This is going to be the after the collision. So after collision, now we're looking at, again, an energy conservation. So I'm taking the kinetic energy is going to be equal to the potential energy. I'm going to use the potential energy to get my final height. So now I have 1/2 4m vf squared is equal to 4mg. I can cancel that, I can cancel that, cancel that. I might have enough room. Then I'm left with 1/2 square root 2gh naught 16 squared is equal to gh. So I'm going to have to do a couple things at once. This cancels, those go away. And then after I undo the square, the g's would cancel too, leaving me with a final height that is going to be h naught over 16. Which, look at that, it's one of the answers.